let's talk about the three mass laws that chemists use all the time. This first one is kind of like the most powerful of the three. It comes up the most often in general chemistry. It's called the law of mass conservation. And so what does that law state? It states that the mass of the reactants, the mass of your starting material, after they react, equals that mass of your product. And so there is no mass that is lost. So let's look at an example. Here we have two reactants. They're placed on a scale, and they weigh a certain amount. We don't know what that weight is. It doesn't really matter. We know that it's one really big weight, a medium weight, and a small weight. Now, if we were to mix these two together and a chemical reaction took place, the mass of that final product has to be equal to the mass that's here. And let's pour these two together. And so we're going to get a reaction. The color changed. There's some solid floating around in this beaker now. But you'll notice we still have the same amount of mass on the right. So the overall mass of this reaction did not change with the reactants or with the products. They remain the same. So this is what the law of mass conservation is. Now I'm going to tell you, I told you that this is a very powerful law. It comes up all of the time in general chemistry. If you're working a word problem, which we're going to start working here pretty soon, if you're working a word problem and you can't figure out some piece of information that you think you need and it's not given in the problem, most likely you can solve it using this law of mass conservation. It comes up a lot. So let's look at another example of a true chemical example of this law of mass conservation. Say we have reactant 1 and reactant 2. They come together to form a product. Now this is just a pictorial representation. The total mass of the reactants is the sum of the reactant 1, the mass of reactant 1, plus the mass of reactant 2. So this gives you the total mass. The product has to have the same amount of mass. It has to equal the same total mass. So these two total masses would be equal to each other. So a chemical reaction, an actual chemical reaction, would be one between calcium oxide and carbon dioxide. This would produce calcium carbonate. So we're going to be talking a lot about calcium carbonate. It's a nice compound that uses a lot of different naming techniques in it. So as of right now, we don't know how to name these types of compounds. However, I just want to give you a few examples where we do use namings, and we're going to start introducing this idea of the atom and naming within the next few weeks. So let's say we had, this is the formula for calcium oxide, this is the formula for carbon dioxide, and this is the formula for calcium carbonate. Within 3 weeks, you will be able to name, you will be able to either write the formula from the name or write the name from the formula. And so within the next few weeks, you'll be able to do that. So let's say we took 56.08 grams of calcium oxide and we added 44.00 grams of carbon dioxide. Now that's going to produce 100.08 grams of calcium carbonate. How in the world did I know that it was going to be 100.08 grams? Well, all I did was I added up the individual reactants, 56.08 plus 44.00. That adds up to be 100.08 grams. So I knew without actually weighing anything that the final product's mass would weigh 100.08 grams. So this is how we use this idea of the law of mass conservation. Very, very powerful law. We'll be using it a lot. So let's look at the second law, the second mass law. This is called the law of definite or constant composition. So what does this law state? It states that no matter what the source is, doesn't matter where the compound is coming from, a particular compound is composed of the same elements in the same parts by mass. Okay, we don't even know what a parts by mass is, so I'm going to show you a few examples of this, and then we'll move on to the last and final law. So let's look at this. Here we have marble. It's a marble statue on the top, and then we have coral here on the bottom. They are both calcium carbonate. I told you that calcium carbonate comes up a lot in chemistry. These are two forms of calcium carbonate. Calcium carbonate is also chalk. The chalk that I use in class, that is calcium carbonate. It is 40% by mass calcium, 12% by mass carbon, and 48% by mass oxygen. So no matter what the material we got this from, either from a statue, from coral, or from chalk, it's going to have that same breakdown. We can look at another one. This is quartz. So here, quartz is made up of oxygen and silicon. And so if we look at the breakdown here, it's 53.3% by mass oxygen and 46.7% mass silicon. And so this is a statue, and this is the crystalline form. Both forms have the same mass breakdown. And so we can perform some calculations by dealing with that percent by mass, as well as a new term called mass fraction. And then we can figure out how much mass of each of the elements was present in a given sample. So this law, the law of definite composition, states that no matter what the starting point is, it's going to have the same chemical breakdown. So let's look at this calcium carbonate. The percent by mass, it's 40% calcium, 12% carbon, 48% oxygen. That adds up to 100% by mass. That makes sense. All of its parts add up to 100%. Now that's the percent by mass. So what is the mass fraction? Well, if this is a percent, the fraction can be found by dividing each of these numbers by 100. So this would be, rather than being in 100%, it would be in a part of 1. So this would be 0.40 calcium, 0.12 carbon, 0.48 oxygen. And if you add those up, you get 1.00 part by mass. So this is the same idea as as when you get a pizza and you add a tip to it. You're just using fractions in order to calculate a certain amount. And so if we want to go from fraction to percent, all we do is multiply the fraction by 100 and we get our percent. Now what we can do is, if we had a 20-gram sample of this calcium carbonate, we can figure out how the mass of each of the elements that are present. We know that the fraction, if we multiplied the fraction by the total amount of the sample, we would get the mass of each of those individual components. So if I were to take 0.4 times 20, I would get 8.0 grams of calcium. If I took 0.12 mass fraction of carbon times 20, I get 2.4 grams of carbon. And if I were to take 0.48 mass fraction of oxygen and multiply that by 20, I would get 9.6 grams of oxygen. I add them all up, I get our 20 grams of the calcium carbonate. And so this is an easy example of using this idea of mass fraction, mass percent, and the analysis by mass in order to figure out the mass that's associated with a given amount of the sample. And now I want to move on to the last mass law. This is called the law of multiple proportions. A lot of students get this law confused with the previous law. I'm going to try and give you two examples where it should show you a little bit better. You should gain a better understanding of how this law is different from the previous one. So if elements A and B react to form two compounds, they have to react to form two compounds. The different masses of B that combine with a fixed mass of A can be expressed as a ratio of small whole numbers. That is a whole bunch of words. So what does this mean? Let's take an example of carbon oxides. So we already know two different carbon oxides, and this was a big study back in the day. We know that we've all heard of carbon monoxide. This is poisoning that can happen in your house. And we've all heard of carbon dioxide. This is the stuff that you breathe out. This is a greenhouse gas. A lot of problems, people are having a lot of problems with this because it is a greenhouse gas. So these are both oxides of carbon. So let's see their mass percent breakdown. If we have carbon monoxide, we're going to learn how to write the formula from the name in a few weeks, but let me just take my word for it. Carbon monoxide is 1 carbon and 1 oxygen. This has a mass breakdown of 57.1 mass percent oxygen and 42.9 mass percent carbon. Now carbon dioxide, on the other hand, has 1 carbon and 2 oxygens. We can do a mass percent breakdown there. It is now 72.7% oxygen and 27.3% carbon. So these are very different mass percent breakdowns, but they're both oxides of carbon. So carbon has has the ability to form two different, or to combine two different ways with oxygen. And that's what we have here. We form two different oxides. So let's see a really interesting fact about this law of multiple proportions. If we assume that we had a 100-gram sample of each of the compounds, we can multiply the mass fraction, which was just dividing the mass percent by 100 grams, and figure out the grams of each of the elements that are present. So for carbon monoxide, it's 57.1 grams of oxygen and 72.7 grams of carbon. Oh, sorry. So grams of oxygen, it's 57.1 grams of oxygen for oxide 1 and 72.7 grams of oxygen for oxide 2. And then for carbon, it's 42.9 grams of carbon for oxide 1 and 27.3 grams of carbon for oxide 2. So what's an interesting fact about this? If we were to take the ratio of the grams of oxygen to grams of carbon, what we would find is we get a number of 1.33 for the first oxide. If we did the same thing for the second oxide, we end up with a value of 2.66. Now the interesting fact is, if we divide these two numbers, so I take the 2.66 grams of oxygen per grams of carbon and divide by 1.33 grams of oxygen divided by grams of carbon, I get a whole number, and I get 2 to 1. What this says is there is twice as much oxygen in the second oxide as there was in the first oxide. So this is a nice little trick that we can use in order to further our understanding of different compounds using this law of multiple proportions.